we are also going to learn how to graph every single log graph and do all the transformations with every single log graph. So here we have the graph of y equals log 4 to the x. And after we do this one, you should be able to do y equals log 2 to the x, y equals log 3 to the x, any base possible. So first of all, we're going to remind ourselves a little bit about exponentials functions. And because this is a base 4, over here, I'm going to quickly graph y equals 4 to the x, because the log base 4 of x will be the inverse of that graph. What are the points that we always knew on an exponential graph? 0, 1. And in this case, you would have 1, 4. 0, 1 is on every single exponential graph, and then the next one is dependent on the base. Since the base is 4, when I plug in 1 for x, I get the point 1, 4. And your graph looks like this and has an asymptote here at y equals 0. So only for this first one are we going to think about the exponential graph. From this point on, when you get a graph for a log, I expect you to go directly to the graph of the log. But if you need to think about the exponential, it's going to help you because the exponential is an inverse. So if every single exponential graph has the point 0, 1, what does every single log graph have?
1, 0.
1, 0. And if on a base of 4 you had 1, 4, on a log of base 4, you're going to have 4, 1. And that should make sense because log 4 of 4 is equal to, well, 4 to what power is 4? 1. And what's going to happen to our asymptote?
It's going to come with an y-axis.
Right? Even our asymptotes, the x and y values change. So instead of having y equals 0, we have x equals 0. And the shape of our log graph and the shape of all log graphs looks like this. So now they ask us to describe certain things. What are our intercepts? Well, there's only an x-intercept at 1. What's the equation of the asymptote? It's x equals 0. Domain. Now, the domain of our log function, in this case, which is x is bigger than 0, notice how it is just a switch of the range of our other function, of our exponential function.
Range you may switch over.
And the range is a switch as well, so that our range is everything. Now, do you still have some space sort of at the bottom of page 378? Is there a little bit of white space at the bottom? So we've graphed log base 4 to the x. If I gave you log base 5 to the x, it would look identical except one point would change. You'd have 5, 1. If I gave you log base 7 of x and you had to graph it, the graph would look the same, and you would have 7, 1. So I'm going to give you another one to graph, but it's going to be the trickiest one yet. It's going to be even trickier than log x. If I gave you log x, it would have what, 1? 10. Excellent. Right? Because that's the common log and it's not written. So I'm going to show you another one where it's not written. So instead of having the word log there, it's ln. And it stands for the natural logarithm. L for natural, N for logarithm. Oh, maybe it's French. Maybe it's like logarithm naturel or something like that. Okay. So the natural logarithm has a base that's not written. Here, I'll write it in white.
2.
No. E. So the natural log has a base that's not written of e. So when we go to graph the natural log, it's not supposed to be any harder. You're still going to have 1 comma 0. It just feels a little bit weird because what's this point going to be? E comma 1. It would still have an asymptote at x equals 0 and still has the same shape as all of our other log graphs as well. So for practicing some graphing, try 10 and 11. And I think on one of them they say do a table of values. You don't have to do a table of values because you can just do these 2 points. If you wanted to do another point on here, on the log 4 of x, what would be the next nice point? Something comma 2? 16. Okay.